Okay, so we're dealing with proportion problems. All of test 3 is proportions. All of test 4 is means. So we're going to have some categorical variables, success and failure. You have to know what all the letters stand for. That's going to be the very first question on test 3, is identify all the different variables we're using for this topic. Because if you don't know the variables, you're going to get every question wrong. You have to know all of our variables. So P, little p, is the population proportion of success. Little q is the population proportion of failure. So those are about the population. Notice they don't have hats. Then what we're going to do is, with confidence intervals, we're trying to estimate P. That's our goal. We're trying to estimate the population success rate by doing one single sample. So we go out and we do a sample and we collect some numbers. We have our sample size, the number of people we talk to or whatever our sample is made of. The actual number of successes in the sample was X. P hat is our sample success rate. That one's a percentage. This one's a whole number. And then our failure rate in the sample. And again, we got to meet all the conditions of the central limit theorem. We need good samples. The sample has to be independent. It's not too large. We have our size conditions. Then the central limit theorem would apply, which means that all possible samples of that size would follow a normal distribution, with the mean sample success rate equaling the population success rate and the standard deviation of all possible sample success rates is square root of PQ over N. So that's all stuff we had before. Problem is, we don't know P. That's what we're after. That's what we're trying to estimate, is the population success rate, and we're just doing one single sample. So we have no way of calculating this thing because I don't know P or Q. That's what I'm trying to get, is P or Q. So we're going to estimate this standard deviation with this object called the standard error. And that's square root of P hat Q hat over N, the stuff we got from the sample. Okay, so this thing's called the standard error. And out of all of mathematics, this is probably the object that has the worst name in all of mathematics. It's a terrible name. This is not an error. Nobody goofed. Nobody messed up. This is, I don't know who came up with this name, standard error. Like, I offer that as extra credit sometimes. I have people go out and people have found it. Like, I could search my email, but I don't even remember who it was. It's a terrible name. It's not an error. This is just our estimate of the standard deviation. It's an approximation of the standard deviation. It acts just like standard deviations. So then we take that thing and we treat it just like we would a standard deviation. If I wanted to say capture 95% of all possible samples, I would go 2 standard deviations on either side of the mean. If I wanted 68% of the population, I would go 1 standard, you know, all that stuff we've done before. But keep in mind that empirical rule we used before was just an approximation. Here we have more exact numbers. If I wanted to capture 95% of all possible samples, it's not really 2 standard deviations. It's 1.96 standard deviations on either side of the mean. And we call that distance from the mean the margin of error. And it's just our standard deviation, our standard error, times these, what we call critical Z values. And we go above and below our sample success rate, and that gives us our confidence interval. So I know I just threw a lot at you. Let me kind of go through that from a different viewpoint. We go out and we do one single sample and we get some sample success rate. If our sample looks good, that should look something like the population. The population success rate should be someplace around there, but we need to leave a little bit of wiggle room. That wiggle room we call a margin of error. You guys have seen this your entire life. Oh my God, if you're watching the news right now about anything, you're hearing margins of error all the time. Every political survey you've ever heard, the success rate or the favorable rate for Biden is 62% plus or minus 3%. That's the margin of error, the plus or minus 3%. And that 62% is the sample success rate. So this stuff we're doing here is quite literally exactly the same as what pollsters are doing right now with political polls. It's literally the same math. It's not like there's something fancier going on in the background. We're doing the same math. So we get some confidence interval that is centered around what our sample tells us plus or minus some margin of error. And then how do we decide how big we want our margin of error to be? That's our confidence level. So we could be 90% confident, 95%, 99%. We can be any percentage we want. These are just the three most common ones we use. And those have what we call these critical z-values attached to them. And then our final conclusion every single time will be something like we are blank % confident that the true population proportion of success is between the lower number and the upper